I can see it. Okay. So good afternoon, everyone. My name is Parthan Nandi. I am a postdoc of NITheCS. So it is my great pleasure to introduce our today's speaker, Professor Igor Pikovski, and he is a distinguished theoretical physicist. And currently, he holds the position of professorship at the Stevens Institute of Technology in the USA, and is also affiliated with Stockholm University in Sweden. Professor Pikovski earned his PhD in 2014 from the University of Vienna, and followed by postdoctoral research at Harvard University, where he was a postdoctoral fellow until 2018. And his research mostly is an interface of quantum foundation and gravitational physics. So Professor Pikovski, please try to join with us, and I think we can start talking.
Yeah, thank you very much. Thank you, Partha, for the really kind invitation.
Thank you.
It's a pleasure. I've never been to South Africa, so that's my first time, at least over Zoom.
Okay.
But maybe there will be another opportunity. But yeah, it's nice to meet everybody. Yeah, and thanks a lot for the interest in this research direction. So like Partha said, my background really is in kind of quantum optics, quantum information theory, with an interest in gravitational physics. And in particular, what type of low energy inputs there could be on the interface of quantum theory and gravity, and also of quantization of gravity. And so here in this talk, I want to talk about mainly a recent result from my group, where we showed that it is possible to detect single gravitons. Is one aspect of this interface, an obvious interface, of course, of quantum theory and gravity. Okay, so let me start with the talk. Just a second, I have to get rid of this Zoom bar. Okay, well, all right. So yeah, I'm a theorist, so I'm not sure what the Zoom bar does. But anyway, as long as it doesn't disturb you, then it's okay. So there's no black boxes or something like that. On your okay. Anyway, so I assume that is fine. Now, okay. So what I want to first a little bit motivate is that there is in fact input from experiments that is possible to the regime where quantum mechanics and gravity meet, and where they meet in a meaningful way. And there's different aspects of this interface that one can probe. Now, traditionally, kind of the experimental access to quantum gravities has been assumed to be, very far away from experiments. And for example, when one thinks about some kind of high energy experiments, which are the typical ways how we access fundamental, at least particle physics at high energies, then obviously the quantum gravity scales that we expect are really far away from reach, something like 15 orders of magnitude away from where we would expect, at least naively, quantum gravity phenomena to arise. Now, there's other ways of trying to probe it. For example, one way which is also very interesting, and there's a lot of research in this, is to try to look at some kind of cosmological or astrophysical observations. And indeed, there is some speculation, maybe modification of Lorentz invariance or some kind of anomalous dispersion of light that might indicate some new physics related to gravity. And that's still interesting to constrain. One aspect of that is that there are no controlled experiments per se, so we're kind of relying on whatever arrives here on Earth, and mostly it's speculative signatures. So it's not really something that we would expect from kind of day-to-day, I don't know how to say, traditional quantum gravity, but rather maybe some kind of speculative new physics that maybe there could be some anomalous signatures that we could at least detect or constrain. And then finally, another aspect is high precision measurement. And that is, of course, the low energy regime. But if we think about high precision alone, so just thinking about that we can make precise tools to measure things, that's also insufficient. So, if you could just compare, say, our best position measurement precision to the Planck scale, we're also similarly 17 orders of magnitude away from what is actually possible to be reached. So what is trying to say is that this brute force methods, saying, oh, let's just increase the energies, let's increase the precision, they're not really the way to reach kind of quantum gravity scales. And this is also why, this has been kind of assumed to be mostly outside the reach of experiment. But, and this is the point of this talk, and I'll give a little bit of an overview, it is actually possible to reach certain regimes where certain effects do play a role. And the idea there is to use novel capabilities with quantum systems and low energies, which is not simply based on precision, but rather going into the domain of physical regime where it's a little bit beyond kind of the standard approaches. And from introducing a quantum information, maybe even quantum foundations perspective, one can ask meaningful questions and also meaningful answers about that there's real experimental input into quantum gravity. And so that's what I want to motivate here a little bit at first. And then later, most of my talk, I want to talk about specifically the ability to detect single gravitons, which is one of the kind of most quantum gravity, most famous quantum gravity predictions. Okay, so what do we mean by this AMO push into new domains? So let me give you a couple of examples of systems that are available in the lab today and that are no longer this kind of traditional realm of quantum physics that we usually focus on or used to focus on before. And so these are real experimental progress, which allows to control systems in entirely new ways. One example is the advent of atomic clocks, where it really is kind of brute force precision, but it is kind of a doubly exponential increase over the last few decades, at least, in terms of the precision we can obtain about the ability to measure time. And so what you see here is really kind of the advent of atomic clocks, first in the microwave regime, then in the optical clock regime. And the improvements have been really steadily over now 5-6 orders of magnitude over just a few decades. And so that allows to ask some interesting questions about the role of gravity, and in particular the effects of curved spacetime on quantum systems, which is one of my big interests as well. By the way, can I ask you if you can tell me, can you see my my mouse?
Yes, everything is.
Okay. Okay, perfect. Right, just in case. Okay, and then another second example is what is known as atomic fountains, which are essentially delocalized superpositions of mass, which can be of very large scales. And so there's essentially matter wave interferometers, which started with something like electrons, but then also neutrons. And today there's cesium fountains or rubidium atoms that can be delocalized over even meter scale separations. So there's examples from the groups of Markasevich, Holger Müller, and so forth, where it's a new domain of quantum physics where the delocalization of a single quantum system over macroscopic scales becomes relevant. And then the third example is quantum optomechanics, where the quantum mechanics is pushed into the domain of mass, namely coming from something like a picogram all the way to kilogram scale mirrors or beyond, where it is now possible to both prepare, initiate, and also read out quantum states, and also apply some quantum control. So it's possible to entangle these systems with each other. It's possible to explore just quantum physics of these large macroscopic collective degrees of freedom and see that things work. And that, of course, opens a lot of new possibilities for fundamental physics, studying quantum mechanics, but also the possibility to study questions related to gravity. And that's what's mostly interesting to me in my group. Now, so what I want to just give a very brief overview. In my group, what we study is essentially quantum sensing, quantum information processing, and its relevance for the interface with gravity. And so there's like something like typical bread and butter quantum optics research agendas, such as how can you control novel quantum systems in new ways, for example, through Rydberg arrays in this example, or also just in general new sensing schemes. So how can you make use of some quantum effects for some genuine advantages in different settings, but then also apply that as tools for questions related to gravity, such as, could we use maybe novel quantum systems for gravitational wave detection, which has some advantages or is complementary to the typical LIGO or LISA approach. So here, for example, we had some work where we showed, you can use superfluid helium to detect gravitational waves, or you can even use atomic clocks in space as tunable kind of narrowband detectors. So this is kind of applying quantum sensing these questions. But then there's also the inverse. You can essentially use the tools that we know from quantum optics and study questions that really are far away from the low energy regime, such as cosmology, and apply these insights. So for example, we recently showed that if you have ultralight dark matter, which is, common models that are now being assumed, such as axions or axion-like systems, then because of their inherent self-gravity and inherent, internal interactions that they must have from just the models they have, and especially due to the gravitational interaction, it turns out that these ultralight dark matter models that are assumed to be classical are actually much more likely to be in a squeezed state. So that's something that we know from PECs or quantum optics in general, but one can transport these ideas or insights into actually, high energy physics as well, where, it turns out that, axion-like models likely populate, if they exist, then they likely populate the universe in some squeeze. Okay, so just to give an example, and then now on the right side, I want to focus on a couple of different directions related to quantum gravity. One is that we can test some phenomenological models, not just from astrophysical input, but also from tabletop experiments. And in particular, using optomechanics or some other tabletop experiments to constrain some speculative quantum gravity models. Another aspect is we can see potentially effects of curved spacetime on the dynamics of quantum systems. So here, gravity is not quantized, but really one needs to take into account corrections stemming from GR, from general relativity, in the dynamics of genuine quantum effects, such as interference of matter waves. In particular, I'm very interested in kind of interference of clocks and proper time evolutions. Then another aspect of our research is just to understand kind of foundations of both quantum mechanics and gravity and how they intertwine, what the Duncan experiments maybe can tell us. And then finally, kind of this new research line of research that kind of just, in some sense, I would say accidentally appeared, motivated actually by my previous work with a group of Keith Schwab at Caltech on superfluid helium detectors. I realized that it is actually possible to kind of change the perspective a little bit and show that it is actually possible to detect single gravitons. And so here in this talk, I want to focus mostly on this aspect and explain how that works and why such experiments can be realistic maybe within a decade or so. Okay, so that will be the main part of my talk. Okay, now, so this is the outline of my talk. First, I want to give a brief overview of just what are the ideas out there, some of them, in terms of tabletop tests of quantum gravity. And in particular, I just want to show a couple of, briefly, just a couple of slides on two examples. One is some phenomenological model where you test the modified uncertainty principle, and you can really constrain it to very high precision. And the other is where people are interested in studying entanglement generation through masses, through gravity, and what it potentially can teach us. And then the rest of the talk, I want to focus on the principle of graviton detection. What do exactly is meant by this? And then in particular, what's the solution, how to actually do that? And it turns out it's actually realistic. The numbers turn out to be such that it can work. And I'll explain some of the key ingredients that are needed for this. I'll briefly connect it to kind of how, why is it that, everybody grows up with the notion that graviton detection should not be possible, but it turns out it is possible. And I just want to make the connection, kind of what is slightly different here and why it works, what's new. And then finally, hopefully there's a little of time, I just want to say a couple of words of what is this first input on linearized quantum gravity one can obtain, essentially in a similar spirit, or motivated a little bit by what are the very first experiments that we had on quantum theory more than 100 years ago. And so that would be a similar type of input that we might have on quantum gravity. Okay, and by the way, if there's questions, I'm not sure, also feel free to ask, or otherwise, of course, I'll take questions at the end. Okay, so let me first give a very brief overview. What are the tabletop routes to quantum gravity that are being explored currently in the last maybe 10, 20 years that has become a rapidly growing new field of research? One aspect of that is to test speculative models. Namely, there could be maybe some anomalous new physics motivated or related to quantum gravity, but which really is something that breaks quantum theory as we know it in some aspect. One popular example is maybe there's some kind of anomalous decoherence, or I call it collapse models. Namely that maybe quantum theory, quantum unitarity breaks down at some scale where gravity plays a role. There have been many proposals, but also some experiments that really, try to explore that. Famously by Marshall et al. More than 20 years ago, but there have been since then a lot of different directions in this kind of gravitational decoherence or gravitational collapse business. But then there's other speculative models that can also be constrained. There's different ideas related maybe to space-time foam or some kind of measure and prepare type models, which are not quantum gravity anymore, but really maybe have some kind of anomalous physics, even at kind of human scales that it could potentially be measured. Let me just give a brief example for this type of example, which is related to my own research now over 10 years ago, where we show that optomechanics can actually constrain some of these models. Okay, so the caveat of these things is that we can constrain speculative models, but still, it gives some input on, how maybe quantum gravity might or might not be. So let me give you here just as an interlude, a quick example. Namely, in many models of quantum gravity, there is the idea that maybe the uncertainty principle is modified at some scale, at some very small scale. And it's interesting because it really arises in a lot of different considerations in Duncan experiments, but also seems to be predictions from even string theory and some other models, where essentially a very common modification has something like this form. Okay, and now why does it have this form? And there is a certain reason for that. Namely, what this functional form gives you is that the product of the uncertainty of delta x delta p is no longer a constant, but it's actually something that depends on delta p itself. And what this does is that essentially, if you plot this minimal uncertainty curve here in red, you have the minimal uncertainty curve in normal quantum physics. What it tells you is that everything to the left of this red curve, these are states that are just physically not allowed by quantum theory. Okay, they would violate the uncertainty principle. And this quantum gravity modification is that this minimal uncertainty curve becomes this blue curve. And the main feature is that there is a gap. And this gap corresponds to a minimally measurable length scale. What it says is that even delta x itself as an absolute value should somehow be constrained physically. We should not be able to measure position maybe to better precision than essentially the Planck scale. You can see there's this beta parameter, beta naught. It essentially tells you where is this cutoff, where is this minimal length scale. Okay, so this is this beta naught prefactor here. So it's a pre-parameter of the theory. And so what these modifications really do is they introduce this essentially the fact that position eigenstates should not be part of the fundamental theory because they have infinite energy, they would collapse on a black hole and so forth. So these modifications are interesting because they arise in these different aspects, but they're essentially phenomenological models in the sense that it still uses kind of quantum language, and you can incorporate them by changing just the algebra of the operators, and then see what happens. So it may or may not be the case that this is how quantum gravity works, but it's motivated in many papers. Now, the point is that about 10 years ago, this bound on this free parameter was very bad, something like 10 to the 30. So this beta naught parameter should be of order 1, but it's actually very, very big, or constrained to be, sorry, it wasn't constrained to be more than it being very big. But what we showed is that, you can actually use some tabletop experiments which operate in new domain and with quantum control to constrain these parameters to much better precision. And the basic idea here is to use optomechanical systems. And if you're not familiar with optomechanics, the basic idea is really the following. It's essentially the ability to interface light with a mechanical resonator which has a large mass. So the basic idea is if you have a cavity, it would store light, but if one side of the cavity is like a little mirror which can be displaced, then the light can change the length of this cavity. So essentially you start with something like a Hamiltonian for the light here in red and for the mechanics in blue, but because the light is inside the cavity, it can be displaced a little bit. So it could move here a little bit, and there's this additional interaction term. Just because the wavelength changes inside, or the fundamental frequency changes inside, and you get this additional interaction, which is basically just radiation pressure between the number of photons inside the cavity and the position of this mechanical oscillator. And what we showed is that, you can actually use this interaction, in particular in the pulsed regime. So if you have like a little pulse coming in and you just kind of make a single shot displacement of the mechanics, you can use that to essentially measure the commutation relation of this mechanical oscillator and see if there might be some kind of modifications. So we came up with a scheme which is essentially like a geometric phase type scheme where you displace this little mechanical oscillator through different pulses in different directions in phase space. And you do it by just timing it in the correct way. And then what you get is you get an overall operation on the optical field, which depends on the commutativity or non-commutativity of the mechanical oscillator. And this is really because you have just kind of 4 different operations displacing it in momentum and in position and in minus momentum and minus position. And you have to, to cancel all that, you have to swap 2 of these unitaries. And when you swap them, you introduce the commutation relation between x and p. And so what we showed is that this scheme allows you to amplify these tiny effects. And it amplifies it through a nonlinearity on this optical field. So if you had normal quantum mechanics, you would get just some kind of self-current nonlinearity on the light. And if you have some kind of alternative theory, so if you have one of these modified commutation relations, which may be there, then you will get a much higher order nonlinearity in the optical field. So you can essentially imprint a signature of possible non-commutativity in an anomalous way from the mechanics onto a system that you can read out very, very precisely. And then you also amplify it here nonlinearly. So there's like several tricks essentially that allow you to do it. It's not brute force precision. It really is just the control that allows you to do it. Anyway, long story short, we just showed that, look, this model could be constrained to very high precision with real experiments. It's a speculative model, but it can give some constraints, at least there's some assumptions. Okay, so this is just to give you an example, and then I just want to say that, okay, there've been a bunch of experiments since then and different type of constraints, actually many in the classical regime where you look for some anomalous nonlinearities. And so now this parameter is kind of more constrained than it used to be, at least for the center of mass portion. Okay, but let me let me move on. This was just as an example to show that, look, there are certain speculative models of quantum gravity where we can really have experimental input. Okay, and that's in very similar spirit. To me, this is in similar spirit as we have, for example, input on, dark matter models, WIMPs, axions, or something else. Namely, okay, this might be null measurements, but they might also not be. It really would tell you, it would constrain some meaningful parameters, which maybe in some cases are well motivated. Okay, but can we go beyond that? So here, the point is, okay, these are null measurements constraining speculative models, and that's good. But can we also see some signatures of quantum gravity as we expected? And here, one of the popular directions in the maybe last 10 years or so in this field have been the study of entanglement generated by gravity. Okay, so this is focusing on what actually real physics predicts, not speculative, but real physics, but in a new domain that we have never tested. And this has been proposed initially by Sugata Bose and many collaborators, as well as Vlatko Vedral's group. And there have been several variations of that, where one looks at maybe some kind of dynamics that is induced by gravity, which cannot be described as just a simple classical channel, essentially. Now, I just to give kind of one or two quick slides of the basic argument here. The idea is this: imagine you create a mass which is in superposition. Okay, so if Earth was in superposition, it would now create a superposition of a gravitational field. That clearly is, very, very non-classical gravity that you would then feel. However, Earth cannot be made in superposition, but maybe mesoscopic systems. So one can now, with optomechanics again, one can now imagine that maybe one has some trapped nanospheres that one can really create superpositions, maybe of masses of around, microgram, and on pretty large scales, like 100 nanometers or something like that. Now, this is way beyond current capabilities, so it's not around the corner, but one can at least, in principle, imagine the technology getting there. And the basic idea is that if you have 2 such systems, they're both in superposition, they should interact gravitationally with each other. And in fact, what this gravitational interaction should do is it should entangle both of these systems with each other. Because they're both in superposition, so they will feel a gravitational force which depends on the distance, and that is delocalized. Now, the basic argument there is that, well, if gravity was some kind of classical entity, in the sense that if it was essentially a classical channel, we know that from quantum information science, by definition, we know that kind of essentially a local operation. So if you just act on subsystems alone and only use classical communication, so just a classical channel, that can never generate or increase entanglement. So that's not possible. So it's usually in the context of something like measure and prepare. Look, if we measure a system, we communicate the outcome to another system. We can never, through this way, generate entanglement. And so here the authors use that as an argument to say, look, there must be some entity that actually generates entanglement through gravity. And in particular, maybe it's a virtual graviton that has to go from one system to another. And then if we actually see entanglement, that means that this underlying entity has to be quantum mechanical. It cannot be a classical system. So the basic idea is there could we gain some kind of indirect measure about the quantization of the underlying degrees of freedom by seeing that entanglement is generated. And so the idea there is like, oh, look, this might give input on the quantization of the graviton. Now, there are some caveats with that, namely, and the main one, and I don't want to say too much about it, the main one is that this picture of this entanglement being generated by the underlying virtual graviton is really not unique. And it of course doesn't appear in the Newtonian limit, but even if you impose relativity, there's many different gauges in which you can interpret it. And in some of them, there is no exchange of virtual particles. So this idea that there must be like a local operation is not necessarily true even in relativity. So this interpretation that it tells you something about the quantization of the graviton is really relatively weak. It's not a direct measure of that. It really depends on like your favorite gauge. And so I have one slide on that, but I don't want to go too much into details. I don't want to derail too much. Just want to say that, look, there's different ways of interpreting it. You can interpret it just on the Newtonian level. What does it mean? So essentially, we create a superposition of masses, creates really a superposition of different Newtonian fields. And that is really something new to test. So that's interesting. There is something similar in cosmology, but it's not exactly the same. And then there's the relativistic perspective to say, oh, well, actually, the Newtonian limit is just a mirage. There really is an underlying field theory. But even then, this local operation is, again, like I said, you can have a local gauge, a Lorentz gauge, in which indeed you have an exchange of gravitons, which are responsible for entanglement generation. But first of all, these are ghost gravitons. These are not the spin 2, but there will be like, basically the spin 0 and spin 1 gravitons, which actually generate entanglement because you are in the essentially in this Coulomb limit of this. But you can also have a non-local picture where there's absolutely no exchange of gravitons at all in this case, and it's just, essentially just a constraint. Anyway, so this was discussed also in other papers. The point is that the indirect tests through entanglement generation depend on additional assumptions. Okay, you can even have some, crazy, absorber theory picture where there's no degrees of freedom at all that generate entanglement. So you don't really directly measure these degrees of freedom of gravity in this experiment. Okay, so this is just to say that there is this very interesting direction of kind of looking if gravity is a channel, which essentially is not a classical entity, and the interpretation of that depends a little bit on what one wants to assume about, initial assumptions. And in particular, I would say there's no input on actually kind of the quantum nature of a quantum particle because it doesn't, of gravity, because it doesn't get involved. And so here comes basically this new research line of research that we introduced. And this is the fact that you can do actually something different as well. And to me, this is a very complementary aspect. It's not instead, but it has nothing to do with detecting entanglement. But instead, what we showed is you can actually observe individual on-shell gravitons, and you can detect them in a realistic type of setup. It's still difficult, but it's completely realistic. So it's possible to have technology that would do that. Like I said, maybe within a decade or two, something like that. And so I just want to put it in perspective. It's not testing speculative models. It's not related to entanglement generation. It's really a different aspect of quantum theory that is also a prediction that it's given, namely that gravitational waves essentially consist of individual gravitons, and one can detect them. Now, what this does is again, it just would confirm the normal predictions of quantum gravity. I mean, maybe if there's some speculative changes, there could be surprises, but we know what the prediction is from regular quantum gravity. At the same time, there's the caveat that these signatures can also be reproduced by some semi-classical model. So if you just detect gravitons alone, this is not sufficient to say that this must be proof that the gravity must be quantized, because they could be mimicked by some semi-classical models, but not all. And then there's prices to pay. So I'll say a little bit more about that later. But just to distinguish, and this is very, very important, to distinguish particle detection from test of kind of the full quantum nature of the theory. Okay, so these are two very separate things. Okay, now, so let me dive now into this main aspect of this talk, where I want to talk about detecting gravitons and how it can be achieved. So first, let me just define what is meant by the detection of gravitons, what is meant essentially by particle detection. I want to clarify this is not our definition, or there's no semantical games or anything like that we're playing. It really is just exactly the same as in all previous literatures that consider graviton detection. So here's a famous example by Freeman Dyson, where he had a paper about 12 years ago, and was thinking about these things also for a long time, where basically his outcome was always that, hey, graviton detection should really be impossible. It seems to be there's no way you can do it. However, I mean, as I will show, the conclusion is incorrect, but how he defines, for example, what is a detection of a graviton is in the following way. He says the following. He says, look, the simplest kind of detector, graviton detector, is, for example, an electron in an atom. Okay, so it's something like, oh, an electron would be excited in an atom from one energy level to another, and that would indicate a graviton if it's induced by graviton. And now how can it be induced by a graviton? He says, oh, we have a splendid natural generator of thermal gravitons, and these energies are in the kilowatt range, and he considers basically the sun as the source of the background gravitons that come and stimulate an emission. So what he means here is stimulated emission in a quantum system. And he calls it, look, the gravitoelectric detector is what is needed. Okay, so he considers essentially the same thing as what we do for photons, which is the photoelectric detector, which excites electrons out of a quantized shell, and the same could be done with gravitons as well, or induced by gravitons. Or a previous paper by Tony Rothman and Stephen Bond, a very, very beautiful paper, by the way, also on the topic of graviton detection. Also, they conclude it can never be done. But they have a very, very thorough and nice discussion and description of this. And there as well, what is meant by the graviton detection is essentially the analogy of the photoelectric effect as a method of detection. So basically, they compute the graviton ionization cross-section for hydrogen, and then they define that as a detector. What comes out is that, it's unrealistic to do it this way. But the key ingredients are the following. What we mean by a detection of a graviton is we want to see a discrete change in energy, which is carried by a graviton. Okay, and that's what it means. That's why you have an electron in an atom, because they have discrete levels of energy, and you want to see just one simple discrete amount of energy. For a single graviton, it will be E equals HF. And the second part is that this has to be extracted from some background. Okay, so it's not about like the input field is just a single graviton. No. The input is, like some thermal radiation, whatever it is. The question is, can we detect a single graviton out of them? Okay, so that's what would constitute a detector, and has always been considered before, but it was concluded that this should not be possible. Now, why should it not be possible? So there's many good reasons why this. So the conventional answer until our paper was that you probably could never detect gravitons, and there's good reasons for this. For example, LIGO detects gravitational waves. And maybe on average, as well, I want to estimate it, they have something like 10 to the 36 gravitons. So it's hard enough to detect even this one wave. So how can we get 36 orders of magnitude better sensitivity? The other consideration is from this previous papers is something like you can compute the cross section of a single graviton interacting with an atom, and it's something on the area of the Planck area. And so from that, one would compute that, and this is what these previous papers do, that if one really wanted to detect only one graviton, one would need something like a Jupiter-sized detector. Okay, and then you can think of some high energy phenomena, and you would just need incredible energies, essentially Planck energies, to reach to see single graviton physics. And so all of this seems to kind of exclude the possibility in any meaningful way, but it turns out it's incorrect. It's correct in the particular context that people have studied it, but there is a way around it. Okay, so incorrect is not the right word, but rather there is a way around these limitations, and this is what I want to present. So this is, if you're interested, this is this recent paper from last year by my students, my postdoc, where we show that gravitons are actually detectable. Okay, so let me first go a little bit through the machinery. So how exactly do we deal and compute graviton detection? And the beauty of it is that it is completely treatable. The linearized limit of quantum of gravity can be quantized in the same way as we do it for electromagnetism, and a lot of the machinery is actually exactly the same as for quantum optics. So one can describe the interaction with linearized gravity essentially through an interaction Hamiltonian in the linearized limit, where in the electromagnetic case we would couple essentially position to the 4 vector potential, so a mu x mu. But instead, in the gravity, this is a tensor coupling. So we couple the stress energy tensor of our system to h mu nu, which is the linearized perturbation of gravity. Okay, so this is a fundamental interaction term which arises in linearized quantum gravity and only in the linear regime. But it allows us with a Hamiltonian now to just treat problems in analogy to everything else we do in quantum physics. So in particular, let's assume that our h mu nu is a gravitational wave. Okay, and we can describe, for example, in the typical gauge, the gravitational wave has just these 4 components with these polarization vectors, only 2 independent components. So there's this polarization tensor, in fact, here. It has this Fourier components, and we just decompose it in some in plane waves Fourier components. Okay, so these are the Fourier amplitudes, and then in theory, at least, we can just impose quantization on this. Okay, so we can elevate these Fourier amplitudes into operators. Okay, and this is what is called linearized quantum gravity. Okay, and so we can do that. We can, in principle, quantize it. The problem is that you can't build a consistent theory when you include nonlinearities, self-interactions of gravitons. But at this level, one can, in principle, do it. And this was done already by Bronstein the first time in over 90 years ago. It has been studied since by many people, and so it proceeds the same way essentially as in electromagnetism, where one just imposes A and A dagger commutation relations. And if you do that, then we can study this interaction Hamiltonian in the quantum regime as well. And one thing one can compute is, for example, something like a transition rate. So imagine you have an atom with a quadrupole transition. And what one can do is one can compute, how what will be the rate of emitting spontaneously a single graviton, just using this interaction Hamiltonian. So I can just apply, for example, Fermi's golden rule, some density of states, and just get an answer. So the point is just the standard machinery as we would do in quantum optics or normal quantum theory, just now with this new interaction Hamiltonian. And in fact, this has been done, of course, many times. And an example is in Weinberg's group on Weinberg's book on gravity 50 years ago, where he has in one of his chapter 10 or something like that, he computes exactly that. He just computes what is actually the rate of emission or absorption of gravitons in an atom. And he just proceeds with this computation. He just plugs in here the wave functions of the electron, and what he finds in this Dij is the quadrupole moment. So it's just you need the corresponding wave functions. And what he finds is the transition rate of this quadrupole transition from 3D to the 1s shell. You can find an exact answer, and you can find an exact number. Now, it turns out this number was wrong. I'm not sure exactly why. He just plugged in some numbers wrong, but in Born and Rothman, they corrected. But still, this number is exceptionally small. Okay, it's something like, the rate of emission or absorption of one graviton, something like 10 to the minus 40 per second. So what he concludes is, needless to say, there's absolutely no chance of observing a single transition. Okay, and so that's kind of the standard answer. You can do quantum mechanics, and then what you find is, gravitons should be emitted and absorbed by atoms, but it's just exceedingly small. Okay, now why is this so small? And so this is actually the core insight, which really on which everything else rests of the rest of the talk. Why is it so small? One example is, let's just take a single harmonic oscillator model for this T mu nu. Okay, so let's assume we just have some harmonic oscillator, relative motion of some mass m that oscillates at the frequency omega. And what we get is, this couples to the relative position of the system in the presence of this kind of passing gravitational wave with amplitude h naught. Okay, so it's just an interaction Hamiltonian now written out in a simplest way for a harmonic oscillator. Let's even assume, okay, this is a very long wavelength, so we don't need to worry about this phase factors. It's perpendicularly polarized, so you just get a very, very simple interaction Hamiltonian between the gravitational wave and an oscillator, which is something like, oh, it's the amplitude of the wave times the frequency and mass of the system, frequency squared, times the relative position squared. Okay, so that's just a standard interaction. Now you can also write it as a cross section or something like that. It's all the same. Now the point is that this is the fundamental coupling of gravitational wave to matter for like a single system, and this h naught is extremely small. So the wave is extremely small amplitude. You know, LIGO detected is 10 to the minus 22, something like that. But also these numbers here on the right-hand side are extremely small. Okay, and you can see that because mx squared is essentially the mass quadrupole of the system. So what is the mass quadrupole of a system? Now imagine we have an atom. Okay, then this mass is just atomic mass. This x is just the angstrom size of the electronic wave function. And what you get is exactly this written as cross section where this is Planck area. In other words, if you want to have a single graviton interacting with a single electron, your cross section is the Planck area. So this is hopeless. And that's essentially what Weinberg and others computed. But the trick is that, of course, that is a very, very bad detector. And you don't need to do it with atoms. And in fact, we know that for the classical detection, nobody tries to detect gravitational waves with atoms. Instead, the idea was to use big detectors. We want to maximize the mass quadrupole of the system. This was the basic idea of Joe Weber, namely, hey, it should be a system with a very big mass quadrupole, very, very heavy and big, and also the basic idea of LIGO, where, okay, you can actually have it much bigger. You can have like these arms far away in free space. And so the idea is to actually, you can make this interaction larger by making your system, the fundamental charge to which gravity couples, larger. Okay, you're not confined to the atomic realm. And this is the essential idea, of course, which is, of course, well known and exploited classically, but we can also exploit it in the quantum domain. Okay, so here is here's a summary of why graviton detection is possible. There are three essential modifications to the thinking from these kind of previous papers or previous ideas in the last 6 decades that actually allow us to do that. And these are three key modifications that I want to summarize. One is focus on macroscopic systems, and in particular acoustic modes of macroscopic systems, which are also quantized. So focus on quantum levels of macroscopic systems, because then you are coupling to a much bigger charge of the system, and you're not limited to atomic realm. B, focus on stimulated emission from the exchange with gravitational wave, which we know now that they exist. In particular, those waves that LIGO is detecting, we know exactly when they come, and we know their properties. And in particular, you can compute that the flux of gravitons per area is something like 10 to the 28. So it's something like 20 to the 28 gravitons per second per square meter that are passing. So we can focus on just the stimulated emission from these particular sources that we know exist and are extremely energetic. And the third and key ingredient is that what one needs to do to see gravitons is you need to see that only a single discrete amount of energy is deposited, because that is the definition of a graviton. So we want to see that we have a detector where only the energy changes by a discrete amount. And this discrete amount should be, according to normal Einstein's prediction from 1905, for electromagnetism, it should be the same for gravitons as well, that it should be Planck's constant times the frequency of the wave. And it's only a discrete package. So the point is that taking all these 3 points together, and only when you have all three, then it is possible to achieve single graviton detection. So these are essentially 3 modifications from these previous considerations. We don't want to do position measurements. We don't want to look at atoms, and we want to look at moments where really a highly energetic wave is passing. And one can show that, heralded on that, it is possible to actually resolve this. And that's what I want to now go into a little bit more detail. Okay. So first, let me focus on point A. So I just want to focus on all these 3 different points. Point A is that we want to focus, and this is the key difference to previous considerations. We don't want to look at interaction of a single graviton with a single atom, but rather with a collective degree of freedom. And so one can either just take, the known Hamiltonians from textbook and just quantize them, or we wanted to be careful, so you can just look at it, kind of basically build it up from the ground up. So imagine you have something like n atoms, okay? Each one of them, we know exactly how to describe them, but there are n atoms arranged in a 1D array, and they're all in some kind of lattice. So they're all, a distance of lattice side A away from each other. And now we want to compute this interaction and then quantize it for each individual atom. Now, this is possible to describe just in a standard way. And in particular, we can find this interaction Hamiltonian, for example, here in the local inertial frame. We find that, what is, it's essentially the tidal force, which is then given by the local Riemann tensor, which is just the fact that, these distances here are essentially squeezed. So as the gravitational wave comes in, then all these distances are kind of changing in the presence of the gravitational wave. Okay, and so this is this essential interaction Hamiltonian. So as xj are all these individual distances, positions, and psi j are these little displacements that each atom can have at each of its sides. But then one can change modes. One can change the how we describe it. Instead of describing it in terms of these n atoms and their displacements, one can introduce new fundamental modes. And these modes are just collective modes, which are this chi L, which are just really just the collective modes of the overall bulk here. Okay, so it's just a change of variable, essentially. And the key point here is that one can see that, there is actually certain subdominant effects. Okay, so each atom is a little bit squeezed, but then there's these collective effects because it's a tidal force that depends on the total mass of all the n atoms and the total length. Okay, so it's essentially, it becomes a bigger effect with the length and the mass of the system, which is of course precisely the point of, like I said, of LIGO and Bar detectors. And so it's not about the individual quadrupole moments of the atoms, but really of the overall collective mode, which now scales up the interaction with both the mass, the total mass, and the total length of the system. And then with having this kind of fundamental interaction with the massive system, one can quantize the interaction. Okay, so one can quantize this H in principle, and what we essentially have is, we just essentially have, the harmonic oscillator corresponding to each mode. This B sub index L is each mode, and that interacts now with the quantized harmonic oscillator of the wave. Okay, and the subdominant term we can forget because it's much lower, but this dominant term here is increased by also the length of the system, so it's much larger. Okay, and then what one can do is one can now compute what are the rates of exchange of gravitons with this overall collective mode of this macroscopic system. And one can find, for example, compute what is the stimulated emission rate in such a system, and one can find it in terms of the system parameters. So instead of mass, length, and frequency of the mode, one can also express it just in terms of the speed of sound of the material. And essentially, this really depends, of course, on the incoming wave, which is very small, but it also depends on the total mass of the system and the speed of sound. And now if you plug in, and by the way, this is of course well known, this is also textbook result, there's nothing new here, it's just that we add the perspective that you can also look at it in a quantum picture. And now, if you take an example, let's say this kind of initial long-standing aluminum bar, the question is, what is the stimulated emission or absorption of gravitons in this case? So if you plug something like 2-ton system, aluminum, and we take the gravitational wave that has already been detected by LIGO, and then what we get is that actually the stimulated rate is 1 Hertz. Okay, so it's actually a very reasonable number. So what it tells us is that energy is exchanged with gravitational waves that we already detected. If we had a resonant detector, then energy would be exchanged about 1 graviton per second. Okay, so there's around 1 graviton emitted or absorbed per second. So not per 10 to the minus 40, 10 to the plus 40 second, not 1 per, but really 1 per second for its macroscopic system. And so it means that there is actually a reasonable time scale where only single quanta of energy should be exchanged. Now, this is only to give a flavor, because the question is, can we actually see that? What we need to do is we need to zoom in on a single event. We need to have detection of the particle, we need to zoom in on the absorption of just a single quanta of energy from the gravitational wave. Is this possible? And until recently, this was completely inconceivable. But this is no longer the case. Namely, one can actually do that by exploiting quantum acoustics. It's a new field where one can actually able to see individual quanta of acoustic energy inside macroscopic systems. It is also possible actually to do it in different ways. If you're at a much higher frequencies, for example, it's also possible to maybe repurpose some oxygen detectors, which has also been discussed here in the paper by others as well. But for this kind of resonant exchange of energy and zooming in on just a single event, one would need some kind of resonant detector essentially in the LIGO band. Okay, so how would we see just a single exchange of discrete energy between matter and gravity? And the point is that it's only the individual events that tell us that there's a quantum of energy that is being deposited. Because if you were to average, let's say we measure just average energy or even average position, this is a continuous number. It can have any value. But the key point of something like gravitons or the prediction of quantum theory is that, hey, they should only come in discrete chunks. And so how is it possible to see it? Well, one would need to resolve only single individual quantum jumps inside the system, a quadrupole jump, which is induced by a gravitational wave. And if it's on resonance, then that means that it really has been an absorption only of a single quanta of energy. Okay, so you need a resonant exchange of energy and zoom in and be able to resolve only one single quantum jump in the detector. And in fact, not in the context of gravity, but in other contexts, this has been done in the past 10 years where people started to resolve quantum jumps in systems, in macroscopic systems as well. So here's a beautiful result in the Michel Devoret's group, for example, where they did it with superconducting qubits, where they can essentially resolve when a quantum jump should happen and then even also control it. Just to mention briefly, but the main point is that if you think about it, what it really is essentially an analogy to what people studied 100 years ago, which is the photoelectric effect. The point there was that, oh, light and matter must be exchanging only discrete amount of energy, and we can see that in the photoelectric effect by essentially a maximal stopping voltage. So the maximal stopping voltage, they didn't need to resolve quantum jumps, but the maximal stopping voltage was giving us exactly this discrete nature of the energy transition. And this is what Einstein explained through, of course, postulating quanta of energy of light. And here's just a beautiful example of Millikan's result on this, I think 1915. It has very clear predictions, namely that, oh, there is like a very specific threshold frequency where you increase the intensity and nothing happens. But then given this threshold frequency from the outside source, then you'll get this increase in which goes exactly proportional to the frequency of the incoming light. Now, of course, in the gravity case, we cannot have light bulbs or like a light source for gravity, but we can just wait because gravitational waves just pass us all the time, and sometimes we detect them. So we can herald on the possibility or on the case where really a gravitational wave is passing, and that's kind of one of the key ideas here. But what needs to be done here is that one needs to be able to resolve these quantum jumps. Okay, one should be able to see quantum sensing of energy. And what I showed before mathematically was just, oh, we computed some rates. This is only to get some kind of feel. Instead, what one needs to do one needs to be able to solve the problem exactly and find what is exactly the probability of only one single quanta, not some averaging. And this, in fact, can be done with this linearized Hamiltonian. It's, again, very similar to the quantum optics one. It's just two coupled harmonic oscillators, and one can solve it exactly. So one can find that there is, the exact unitary, which describes how this proceeds. If we assume that the gravitational wave is, highly energetic as it's passing, essentially given by some coherent state, one can find the exact answer. And one finds that, look, the detector is actually what it sees when the gravitational wave passes is some kind of displacement operation on its mode, which depends on the detector property and also the wave property. Okay, so one can solve it exactly. And then if you solve it exactly, the main signature of gravitons is this probability. It is if you start, say, in the ground state of our system, what is the probability that we exactly herald on only one excitation? Okay, so can we resolve one excitation, and what is the probability of that? And one can, again, compute it. One can actually find that, oh, there's always a maximal probability. So there's some ideal, basically, detector given a specific waveform. And we can, that depends on the waveform through this kind of complicated integral. But we know some of the waveforms from LIGO detections. And so we can find essentially an ideal detector or ideal detector mass in order to optimize just a single quantum jump inside the detector, meaning the absorption only of one quanta of energy for a given gravitational wave and detector. Now, the point is that it might still not work because maybe these numbers turn out to be really bad. And for most cases, so now I'll give you a table, for most cases, namely for most sources and many kind of detector designs, it is indeed really outside the reach of experiments. So here, for example, if you just have black hole mergers so here, these first four is what LIGO has detected. These are the sources. And this last four columns are speculative sources, maybe new physics, like some kind of primordial black holes or something like that. But focusing on just known sources, such as LIGO detections, the black hole mergers that LIGO mostly detects, they're really hopeless. It seems to be hopeless to detect single quanta of energy from them. So for example, you need something like a ton scale detector. So you need a detector resonant with the system, with the wave, and to be something like 10 tons. And remember, now you want to resolve a single quanta of energy as if you had an atom. And for these masses, this is hopeless even for optomechanics. Okay, so optomechanics operates like in the gram range or below. But it turns out, so if you had speculative sources at high frequencies, then it would be much easier. But who knows if they're there? But in principle, high frequency gravitational waves, if they exist, it should be easier to extract one quanta of energy from them. However, the nice thing is that there's one type of source for which it seems really reasonable, and it really exists, and that is the neutron star merger that has been detected by LIGO. It turns out that the neutron star merger, it just goes through this resonance much, much slower. It's just very slowly chirping gravitational wave. And we found that for this type of system, if you had a mass on the order of kilogram scale, and it was in the dilution fridge of a millikelvin or something like that with high Q factor, then for this system, you would actually be able to extract only one and only one quanta of energy from the wave. So it turns out that for some sources, it is actually possible to have such a detector, and the requirements are not too bad. So here, for example, if one were to compare what are the requirements for like temperature and Q factor to what people already achieved in these bar detectors long ago, it turns out it's something like 2 to 3 orders of magnitude beyond to what people had 20 years ago or 30 years ago. So these lines here are, depending on what it's made of, this is where you would need to be, we would need to be able to resolve one quanta of energy. And these points here are detectors they had and we're planning to have. So it's still some technology development, but it's really just, maybe 2-3 orders of magnitude beyond what people already had in the 90s. But the main challenge really is not just simply the noise reduction, it really is the quantum sensing. Namely, what I explained before is you really want to see only one quantum jump of energy, and that is challenging. However, what comes to the rescue is, again, quantum technology that has been developed in the last 10 years or so. And so here, let me give you one example. This is actually even longer ago. Here is a demonstrated measurement of energy of just actually just light. So this is a Rydberg atom. This was done in Serge Harosh's group, where he sent Rydberg atoms that interact through a so-called QND interaction, meaning they couple to energy. So they couple to individual photons inside a cavity, and then they read out these Rydberg atoms in order to deduce how many photons are there actually inside the cavity. So what you will see here is just a quick video where they basically count photons inside a cavity one by one. So these are really kind of single quanta measurements of light that they've been doing. So let me just run it. I think it's 1 minute or something like that. So what you see here that initially there's some populated cavity, and then slowly these photons decay. And this is the reconstruction by continuously measuring these kind of Rydberg atoms that go through, which serve as detectors. They continuously monitor the exact number of photons inside the cavity. And over time, there's something like 3 photons there, and then they decay. And now there's a reconstruction that, okay, now we have 2 photons exactly. And then after a while, it will be the teal aspect where all photons basically leaked out of the cavity, and they can see that this is essentially, now zero photons inside. So this has been demonstrated for photons. So QND measurements of energy are kind of standard practice for photons. But what we needed, can we do it in a massive system? Okay, so now we need to do it in a system which is, kilogram scale. And it turns out that actually that is now being done as well at somewhat related scale. And this is called quantum acoustics. And so in quantum acoustics, what people do in many different devices is to measure actually individual phonons inside the system. And what one has to do is you always have to have some kind of nonlinear element. So here, for example, in the Rob Sherkop's group at Yale, they have some SAQuTI, which parametrically couples to the excitations inside the substrate, and there they could really see, I think, one of the first experiments where you can see really resolve individual phonons inside the system. There are also a similar system here, this drum resonators with a LC circuit, where they can really resolve individual. Also, it's a piezoelectric system where individual phonons, individual quanta of acoustic modes are actually resolved. So here they can see, look, they can resolve if it's exactly 0 quanta or 1 or 15 or 30. So they can actually measure exactly in this Fock basis. And more recently here in Yiban Chu's group from ETH, they've demonstrated the same capability where they can really resolve 0, 1, 2, 3 phonons in a system which is millimeter scale. So in terms of mass, it's something like, I think, close to milligram, maybe 100 microgram scale, something like that. So systems as heavy as milligram or close to milligram have actually now the capability of resolving individual photons. And that's all one needs if we are on resonance with a gravitational wave to see, hey, there is one excitation that has been excited by a passing wave. Except we need it now in a kilogram range. So there's still like 5, 6 orders of magnitude to bridge. But this is certainly possible, even with some thinking to make it more realistic and there's some technology developed. Or with superfluid helium, people have done similar things as well through optical reading. Okay, anyway, so this is just a simulation. I'm not sure, I think I'm probably running out of time. This is just a simulation, how this would look like, where you basically monitor. You have something like a resonator. You have to be resonant with a wave. You don't know when the wave passes. You just have to keep it ground state cooled, and then you just monitor. You just keep measuring, like in this Harosh experiment. And you keep measuring energy, and most of the time nothing happens. But here, for example, here in this B aspect or B's, you see what is the probability to be in the ground state? It suddenly drops, and the probability to be in the first excited state suddenly comes out. So if you heralded it, oh, that was exactly when the wave passed, that means that, oh, this was really the absorption event of a single quanta of gravitational waves. Okay, so here, let's say the summary of this part, and then I don't know how much time I have, but a summary of this part is to say that single graviton detection is possible, and the point is to go away from the atomic realm to look at macroscopic quantum systems, but one needs to also look at stimulated emission absorption in the presence of LIGO detections, which now can be done because we know when they detect things, and one needs to really sense quantum jumps. So one really needs to be able to sense energy and not position, and that is essentially counting phonons. That's what one needs to do. And then, only if you cross-correlate to classical detections, then okay, this was really induced by a gravitational wave. Okay, and so with all these taken together, it is possible to detect single gravitons. It's maybe 4 or 5 orders of magnitude beyond current capabilities, but it's not at the Planck scale, and it's not 40 orders of magnitude away. Okay, so in other words, so Dyson speculated it might never be possible, and it turns out it is. So there's many ways how it cannot be done, but there is some way in which it can be done. And in particular, it has to be a resonant exchange of energy, and it is through essentially the E equals HF, or the photoelectric effect formula, which was the insight of Einstein, that this indicates there must be quanta of light. Now, can I ask how much time do I have left, or am I completely out of time? Unless everybody left already, or I put people to sleep. So they still have 5 minutes or so. I'm not sure. You're all muted. Okay. Well, if nobody's stopping me, then I'll just continue for 5 more minutes. Does that sound good? Okay. Well, nobody says no, so then I'll do that. Okay, so now I want to, there's one important aspect, namely detection of gravitons is not the same as proving, or really fully proving, the quantization of gravity. And this is exactly the same as it was also for quantum optics. Namely, the photoelectric effect is the starting point. And if you know, for example, 2 years ago, we had the Nobel Prize, or 3 years ago, for loophole-free Bell test. Okay, so we went a long way from the photoelectric effect all the way to proving quantum theory through Bell tests. There is a sequence of certainty, essentially. So this detection of gravitons is just the first step. Now, why is it not a proof of quantization? And that is because there are certain semi-classical models which can reproduce it. And that's exactly the same as for the photoelectric effect. Namely, the best explanation is essentially Einstein's formula for single quanta, exchange of quanta, but there's alternatives to it too. And in particular, you could have something like an effective semi-classical Hamiltonian, where you just have randomness inside the matter, and the gravitational wave is not even quantized. So this model is not ruled out. It's possible that this can also be explained. However, ruling the semi-classical model, I mean, for example, in optics, we would need something like anti-bunching experiments, or see like sub-Poisson statistics. These are modern tests that go beyond just simply detection. And in particular, you would need something like an input of like a quantum state input. This is irrelevant for what we are looking at. Namely, for just detection, we cannot rule out this model, but that's also not the goal. What's important to remember is that this model is not normal wave physics. I think this is really a critical point. Namely, yeah, this model could explain graviton detection without gravitons, but it's not classical physics anymore. This is not what you would expect from normal wave physics, because normal wave physics does not reproduce, the threshold frequency and increase in frequency, just as Einstein realized. But this model instead is energy non-conserving. So it violates conservation laws, because you have individual clicks. Essentially, you induced clicks in the matter, but the energy comes from nowhere because you didn't have gravitons. So where did the energy come from? And this model can't explain it. So in other words, yeah, this model we can't rule out, but it's a very pathological one. It's not normal physics. So it's not the goal. Graviton detection does not necessarily mean that you have to rule out this model. It's just the first step. We can detect particles. And then, maybe in 50 years more, maybe there's a way to detect something like anti-bunching, where it's not anymore captured by this model. So I just want to clarify that graviton detection is not proving quantization, but if you want to explain it without quantization, there's a very big price to pay. Okay, so then you have to be really in this kind of very weird conservation law violating regime. Okay, and just to give you like the right picture, when we have photon detection today, it's exactly the same as what we explained here with graviton detection. Every photon detector is essentially a photoelectric, it's a cascade diode where it's an on-off detector. Okay, so what we do is we just do particle detection, but we're not testing beyond that this particular anti-bunching behavior, just as normal single photon detectors also don't do. Okay, all right. So let me just skip over the analogy. I just want to say, is there still something that we can learn about the quantization of gravity from this, even though it can be explained semi-classically? And the clear answer is yes, because this is a very specific model. We can't rule that out, but there's many questions about quantum gravity that we can answer, and many anomalous physics. And this is something we actually studied with some high school interns, inspired by very, very first days of quantum theory, where people were asking the same questions. And it was a fun project. We also won like a prize from the Gravity Research Foundation on this. And the summary of that is the following. So what could be some of the simple tests? If we had a graviton detector, what input can it give to linearize quantum gravity? And here are 5 examples of input. First of all, essentially what we're doing is we're probing this interaction Hamiltonian. Okay, we're probing this interaction Hamiltonian in the quantum limit, where really only single quanta are exchanged between these 2 parts. So one question is, could the energy content in the graviton actually be different? Or in other words, could maybe the Planck's constant be different in the gravitational sector? And that could indeed be the case. And if so, then you would see essentially like, bigger energy transition than you expect. So the quanta of gravity could be, maybe different than the quanta of light. Could it be universal? This is the type of questions they asked back then in many experiments in the 1910s and 20s. Namely, is it the same for different type of systems? Also, is it the same for stimulated emission and absorption? In quantum theory, there's a very intricate detailed balance between emission and absorption. And now, is it actually the same for the gravitational case? So you can look at emission or absorption, and the probability should be equal if quantum theory holds. And then finally, you can also ask if it's a spin-2 transition. Okay, because if a single graviton was not a spin-2 transition, it would excite the wrong mode inside the system, because there's still the quadrupole nature is still imprinted inside which transitions are allowed. And then, of course, we can combine it with other experimental inputs to maybe rule out more. So in other words, this graviton detection, A, would be a milestone in just detecting the particles as we expect them, but B, it would also test a little bit about whether these expectations are exactly right. Okay, so they could be different. Is it spin-2? Is the energy correct? So there could be some anomalous physics, which is not linearized quantum gravity, which would be different. Okay, so with that, I apologize, I'm a bit over time. I want to say, that's why I call this talk Demystifying graviton detection. Everybody thinks it's not possible, and so did I, everybody. However, it turns out this is incorrect. It really is possible. It's much, much easier than we thought. It's still not easy, but it's much, much easier if you think about it in the right way. So we really need to extract one quanta of energy from the gravitational wave, and that's possible to do with specific system. You just need to be resonant. It doesn't even have to be a bar detector. It has to be some resonant exchange and energy measurement. Now, it has been overlooked in this context because whenever people thought about gravitons or quantum nature, they always thought about detectors which are traditionally quantum, like atoms. And for atoms, it's really hopeless because their charge to gravity, coupling to gravity is too small. Gravity detection is not a proof of quantum gravity, but it can test some aspects. There's always, there's never a proof. Just as quantum theory just keeps being tested more and more, similarly here, it would be the first step, like we're in 1905 and not 1995. But it can test some aspects of gravitons. Okay, and with that, I want to thank, of course, also my group and especially you for your patience and attention. Thank you very much.
Okay, thank you, Professor Igor
Okay.
Pikovski, for your nice and very interesting talk. This is the time for questions and comments. So, are there any questions from the audience and online audience? Please ask by unmuting yourself.
Hello, sir. So, thank you for your nice talk. I have a
Are there any
question.
questions?
Yes. Can you hear me?
Yes, I can hear you. Thank you.
Okay.
Yes,
So,
please
thanks
ask
for
by
your
unmuting yourself, Ms. Nandita.
yes. So, thanks for your nice talk. So, I have a question that does your analysis connect in any way with
Can
the
you hear me?
Debye-Waller? Yes, I can hear you.
Professor,
Yeah,
can you hear me?
I can hear. Yeah, I can hear the question.
Okay. So, does your analysis connect in any way with the Debye-Waller factor that appears in X-ray or neutron scattering from crystals? Since that also involves how lattice vibrations suppress coherent transitions, could it affect the graviton resonator coupling too?
Yeah, well, I mean, maybe indirectly at some level, but to leading order, no. because the coupling physics is very, very different. From a gravitational wave, the coupling physics is, look, you're trying to shake or you're trying to move the space apart, but all the atoms are resisting because they interact with each other. And so this kind of the factors about the for what usually is relevant for like electromagnetic interactions are not directly relevant for this interaction strength per se. But I mean, of course, some internal physics of materials does matter, maybe for some imperfections, or maybe they go into the Q factor, but I don't think there would be directly, I don't think there would be something analogous to this kind of the bivalor factor here, because it really is just, hey, can you excite an acoustic mode just like in the normal bar detector picture? But I have to think a bit more about it. I don't know if that answers your question fully.
Okay, thanks for your answer.
Okay, are there any other concern, any comments?
Hello.
Yes, hello,
Yes,
I can hear.
Hello. So, so I'd like to ask a question.
yes, you can ask.
Hello.
Yes,
Yes,
we can.
we can hear you.
So,
Yeah.
can you hear me?
Yes,
Yes.
we can hear
Can you
you.
hear us? Yeah, you can ask your question.
So, just like you commented that we are in the bath of thermal gravitons emitted by sun, emitted from sun. So instead of detecting a single graviton, can we measure a spectrum of thermal gravitons like the Planck spectrum in case of black body radiation? In that case, if I get a spectrum like Planck spectrum, it will at least establish that gravitons is absorbed or emitted in terms of single quanta rather than as a continuous.
Yeah, this is a very good question, and the Planck spectrum would certainly be very interesting to measure. The problem is, I mean, I don't know how. Maybe there is a way. The problem with the sun or other thermal gravitons we expect to be there is that it's an extremely bad source. That's one of the, Dyson considered it, but it was before LIGO detected anything. So if you compare these violent mergers, there's something like I said, there's something like what passes here, something like 10 to the 28 gravitons per second. And this is way, way, way more than any thermal bath of gravitons from the sun. So we just too weakly interact to see them. So I think it's just not enough flux from, even though the source is very close, they just, it's just not enough energy inside this gravitons from the sun to be able to see that, as far as I know. But never say never. So I'm not sure how, but at least naively, it seems to be extremely subdominant. That's why LIGO doesn't detect it either. They detect these black hole mergers because the energy in that is just humongous. It's just incredible. So yeah, I don't know how it could be sensitive to like a thermal bath.
So suppose we can theoretically model a thermal spectrum, a frequency versus intensity curve of the gravitons for a thermal source. Then can we use matched filtering technique kind of thing to detect whether it is there, although it is very weak.
I mean, it's just
Using
too weak.
matched filtering
I mean,
technique.
it's just too weak. I mean, what I mean is, I don't know exactly numbers, but like, we know LIGO, for example, detect these amplitudes if they're 10 to the minus 22, say. So 10 to the minus 22 they can detect. But I think any of these thermal gravitons, there's something at 10 to the minus 30, 10 to the minus 40, something like that, as far as if I remember correctly. So there's no techniques that can help you if you're just, not sensitive, if they're just too weak. But maybe there's a way. I just don't know. I don't know at the moment of any.
Another point, just looking at the slide now, it is open. So one way, the LP, the cross section that you have calculated, what value of omega is assumed here, is taken here? What value of the frequency is taken here?
You mean this cross section? Yeah,
this
so
cross
that's
section. Yes, yes, yes.
yeah. So this is for an atom. So
Eh,
if you were to plug in just a single electron, so you have like an electron frequency, you have electron mass and angstrom, then you get this. This is what people quote in the literature, and that's just for an atom. So because sometimes you just have these statements that, oh, like cross section is so small, but that's only true for an atom.
Yeah, but I was thinking that if there is any way of increasing this omega to compensate this small number.
Yes, there is. I mean, atoms actually have, the optical transition at 10 to the 15. So it is actually in here already. But there's no sources at high frequencies. So you want to be resonant with like a source, and the sources are like kilohertz.
Okay, are there any other questions from the audience? I think Detoni Adamas,
Yes,
please
thanks.
unmute yourself.
Can I ask a question? Thanks so much for the great talk. I was just wondering, to extend your analogy of sorry, I seem to have an echo.
Yeah,
Quanta,
I still hear you. I
can
think.
you mute yourself? No, no, not you, Igor. There seems to be two Papa windows. Okay, I'll just. I actually put my comments in the comments if that's easier. I just thought, have you extended your analogy about the photoelectric effect to looking at something like the superradiance, which scales up single photon effects by having collective interactions, so lots of coupled oscillators, but for acoustic modes, not.
So the short answer is it's a very good question, I think, and I also think that's an interesting direction. We have not done that yet, but I think that is a valuable direction to explore. So we also thought about this, namely, like, look, here we're just really just doing it kind of very orthodox or conservative, like, hey, we just take like you just whatever, just normal acoustic modes, but maybe you can really exploit actually something like super radiance or something like that for this, which would indeed be
Almost
very
as though
interesting.
you're developing something like quantum cavity.
Yeah, exactly. Or cavity acoustics, but then it would help for quantum, right? Exactly. So I think this is a very interesting question, and yeah, I don't have
Thanks.
a good answer yet,
It
but
was a
hopefully.
really interesting talk. Thanks.
Okay, so Prof, I have few comments on your talk. So the point is that, as I understand, in your system is a macroscopic quantum system and allowed to interact with the gravitational environment with the gravitons. So how you can avoid the environmental decoherence in your macroscopic quantum system?
Yeah, it's a good. Okay, so but first of all, it's not about the entanglement here with the graviton. So somehow, there's many different aspects of quantum mechanics. Here, what we mean by graviton detection, or what is meant, is really, hey, you want to see, is energy discrete? Okay, so quantum mechanics has many predictions. And this other aspect I mentioned was entanglement generation. Yeah, that was different. But here it's like, hey, is energy discrete? So there's no entanglement generated here. It's just like, hey, do you see clicks? Click, 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 rather than like a continuous prediction. And that answers a little bit your second question, which is very natural. You say, like, look, you want to be in a quantum regime, don't you decohere? And it's yes and no. The beauty of this is that you're not as, let me try, you're really not as prone to decoherence as, for example, superposition experiments. So these other types of experiments that people consider, you really need big masses in superposition. And for example, Professor Petruccione would know extremely well how extremely difficult this would be. So there's like, of course, a lot of theory of decoherence, which essentially is near impossible to have these large superpositions. They nearly instantly decohere. There's so many ways how the information can be carried away. It would decohere. You're right. But the beauty for graviton detection, the state preparation is actually very trivial. All you need is you need to create a single energy eigenstate. And for that, it's enough to be ground state cooled. So in fact, you just need to cool. So it doesn't decohere, it won't dissipate. So it's governed still by the Q factor and the environmental temperature, absolutely. But it's not as radically exponentially bad as decoherence. It really is just energy dissipation. So essentially, you just need to ground state cool. and you're not prone to decoherence there if you're in zero. And you have to make sure that, you don't excite your system for too long. So what we computed is like basically a duty cycle. We said something like, look, the gravitational wave, neutron star wave passes, it maybe takes a few seconds. Let's say we want to keep our system in the ground state for 100 seconds. And then what are the requirements? So we find, you need a millikelvin and Q 10 to the 10. So it's more than they had, but it's not too bad. It's like 2 orders of magnitude beyond noise suppression they had. But you of course never know when the wave comes. So you just keep your system coherent for 100 seconds, and that's reasonable. People already did ground state cooling for these masses. Maybe it's maybe 1 second only, not 100 seconds. But then you need to repeat it. You never know when the wave comes. So in some sense, the decoherence is not a problem. It's really the measurement. Like, can you really resolve quanta of energy at these time scales? So kind of the challenge is a little bit twisted. In normal, you would think, decoherence kills you. But no, decoherence here is okay because you just need ground state cooling. But the quantum sensing part is challenging.
I see. Okay. And my other comment is that, do you believe that the entanglement from the gravity can indicate the quantum fingerprint of gravity? Because you have mentioned initially that there is something related to the entanglement harvesting from the gravitations. In fact, the Newtonian gravity.
Exactly. So again, that's not related to the graviton detection, but there's this other research direction, which is detecting entanglement through gravity. And I think it's ambiguous. I think it can teach you some things about gravity, but I don't think it's you need additional assumptions to say, hey, this really is due to some kind of quantum gravity. That's what I was saying, that, okay, you can choose some gauge and compute how entanglement is generated. And then, in this gauge, it really is generated by gravitons, virtual gravitons, and you need to quantize them. But if you choose a different gauge, then that's not the right picture. Entanglement is generated differently. So I think it's ambiguous. If you just measure,
but I think in my opinion, in this regard, if one can show that two spatially separated objects, there are no direct interaction between them through the gravitation, but if entanglement harvesting through the vacuum fluctuation of the gravitons, then one can justify that it is an entanglement really due to the quantum nature of gravitation in some way.
This might be true, but this is a slightly different setup, right? So there's no direct Newtonian. So here there's a Newtonian interaction between.
Exactly. Here it is impossible.
That's right. And you want to, really have them far away, interact with the gravitational field or vacuum, and then extract. Yeah, I mean that might indeed be the case. However, that really
I think
science fiction.
In fact, in this particular context, this LOCC principle required the local interaction. But you see, when you introduce the Newtonian interaction between two massive objects, it's no longer with a local interaction in the Hilbert space. It's a non-local operation on the Hilbert space.
Absolutely, exactly. That's my point as well. And like I say, even in relativistic, even beyond Newtonian, even in relativistic,
exactly.
Yeah, it's also a non-local interaction on the light code.
As an event, they are local, but it's not maintain the system locality.
Yep, exactly. You're right, and that's why it's only if you impose this very specific local kind of Feynman gauge essentially. Then okay, if this is really my true underlying ontology of nature, then this part has to. But relativity doesn't impose it. You can, exactly. That's the point. That's why I mean this interpretation is ambiguous for these type of experiments. But there could be variations, like you say, where maybe where indeed actually you really tap indirectly into this quantum nature.
Thanks for this clarification, and it's really a nice and interesting and insightful talk, and we learn a lot of things from your conversation. And I think we have no questions and comments from the audience, and we can solely stop here. Thank you, Professor.
One quick question. I think I have there's one question. I'm just looking in the chat. Somebody, Conrad, I don't know if Conrad is still here.
Not really.
Yes, I think so. Yes, I think it's still in the partition. Anyway, I can just quickly answer this. If I'm aware of groups, if you're aware of groups currently working on the experimental test of quantum gravity, yes, well, different aspects. So I think actually on this slide, there's a good summary. So there's nobody at the moment working on graviton detection because it just didn't exist. There was no such field. But I'm hoping that this is now changing. I think there's many groups that might be interested to think in this direction. But there's some groups that are
one thing I would like to mention in this regard, I think I should mention my group, in fact myself, are investing our research to the indirect evidence of graviton through some another point of view. I will just make a comment in this point.
Yeah, exactly. So I think there's a lot of groups interested in this now, and there's a growing field and many theory ideas, but also some experimental. So really some experimental as well, where, I showed already this tested speculative models. There's many experiments there. I mean, I showed this commutative deformation. There's experiments testing if it like unitarity is broken down. There are actually many experiments in this direction, and people plan more. And then there's some towards entanglement generation and so forth. So it's somehow, yeah, there is some input. There's different ideas, some input on speculative models, and also coming up, hopefully soon, input on kind of the real stuff. So yes, there is experimental quantum gravity. I think is certainly going to be a growing field in the next few decades.
Okay, thanks for your comment. Okay, so we can stop here for today. Okay, please send your slide to my email. It would be very helpful for us. Okay.
Sure. Yeah. Thank you very much. Thanks for your.
Thank you. Bye bye.